Hello friends, so in this lecture we will focus on the air exchange or the ventilation rate because it's actually an extremely important parameter when designing the indoor air quality. So when framing the ventilation guidelines, it is important to look at the exchange rates, and this is basically as we have seen earlier, this is the number of complete air exchanges that can occur per hour. Mathematically, your ventilation rate, which is volume per hour, can be calculated as Q equal to A times V, where V is the volume of the room and A is the air exchange rate or a rate constant. Basically, how many times the volume of air will be exchanged in a particular, what will be the volume that will be exchanged per hour? What is the fraction of volume V of the room exchanged per hour? Is it half of the volume exchanged per hour, or full volume is exchanged, which means complete flushing per hour? So A times V will give us the meter cube per hour ventilation rate. Often the standards are designed as liters per person per second or liters per square meter per person per second. This is because how much a person emits, and then also sometimes you have to see how many people are there in a particular given area. So one person will have less amount of space. In a smaller area we may need more ventilation. In a larger area of a room we may need a lower ventilation given the same amount of people. If we have two people in a hall, maybe we are okay with less ventilation, but if there are two people in a small hostel room, we maybe need more ventilation. The key is CO2. CO2 is generated by building occupants in accordance to their body size and activity. So is it an adult or a child? Are they doing some rigorous activity or non-rigorous activity? So the prevention of buildup of CO2 is a motivation factor behind increasing the ventilation. CO2 in fact also acts as an indicator of the status of the ventilation and the overall ventilation rate. If we have more buildup of CO2, which basically suggests that there is a less or a sort of poor ventilation. If there is less CO2, then we have a less buildup, and maybe there is a more ventilation or a higher exchange air rate. This is basically fresh airflow per person QP as a function of GP, which is the metabolic CO2 generation per person in a particular zone, which depends on age, gender, body weight and surface area. CSS is the steady state indoor concentrations at a given occupancy and activity, and CR is the CO2 concentration in the replacement air, the air that is coming and flushing the room. We will bit derive this air exchange rate or air exchange rate constant mathematically in the following uh, slides. First we will describe the setting, which is one particular room, and there are some people inside the room which are emitting this CO2. This leads to the concentration CT. A replacement air CR is coming in and CO2 containing air is going out, and this is the air exchange rate 1 minus the ln 1 minus CT minus C0 divided by CSS minus C0. And sometimes when we have a built up phase, which means uh, the people come in and we open the room and let the ventilation happen, we might be having a build up in the CO2 because the people are acting as a source. Now let us derive this term. So I'm going to open our whiteboard and do the derivation. So let us go back to our familiar mass balance schematics. We have F in mass flow rate coming in the room. Room has a mass of the pollutant, in this case CO2, as mt, mass at any time t, and concentration at any time t, and mass is related to concentration as mt is equal to V times Ct. What is F in? F in is equal to the flow exchanged with the room, which would be our air exchange rate multiplied by the volume multiplied by CR, the concentration in the replacement air. So we have a term CR here. Then as there are people inside the room, we have the term emissions. Now the air is going out of the room. So our F out will be there. And F out will be the volume of air going out, so A times V, and the concentration in this air, which would be C at time t. This is it. Now we are going to set up our mass balance equation. So we have d m t by d t. This is equal to, if we look here, this is v d c t by d t. So that's the left hand side, and the in sources will be a v c r plus e, and the outgoing sink is a times v times c t. So I'm going to bring the v to this side, and we get dct by dt is equal to avcr plus e by v minus a c t. Now I'm going to give this term some nomenclature. So right now I'm going to say, let P be equal to A V C R plus E by V. So now the dC by dt equation comes as dC by dt equal to P minus A C T. So the solution to this equation would be C at t is equal to C0 e to the power minus at plus P by A 1 minus e to the power minus a t. This is very similar. This equation is very similar to our that equation dm by dt equal to E minus Km that we saw in the mass balance lecture. So our solution is also this, very similar. Here the solution was Mt equal to M0 e to power minus Kt plus E by K 1 minus e to the power minus Kt. So our solution is very similar. Ct is equal to C0 e to power minus At plus P by A e to power minus At. So at steady state, our T is basically tending to infinity. So CSS will be, so this term at T going to infinity, this term will go to 0, and this term will also go to 0. So CSS will be basically P by A. So now Ct is equal to C0 e to power minus at plus Css 1 minus e to power minus at. So our simplified equation becomes C at t equal to C at 0 e to power minus at plus Css 1 minus e to power minus at. Now we are interested in solving for e to the power minus, basically we are interested in solving for a. So let us rearrange this equation. We will have e to the power minus at C0 minus CSS. This will be equal to, so C0 minus CSS. This will be equal to Ct minus CSS. Or we have e to the power minus at is equal to CSS minus Ct divided by C CSS minus C0. So I basically just multiply both sides by minus 1. So this becomes CSS minus Ct. This becomes CSS minus C0. This can be rewritten as 1 minus Ct minus C0 divided by CSS minus C0. If we were to bring this as CSS minus C0 plus C0, so we will end up with the same scenario. Now we can take the ln on both sides. So we will have minus a, I'll just do it again. We will have minus a t is equal to ln of 1 minus Ct minus C0 CSS minus C0, or a is equal to minus 1 by t ln of 1 minus Ct minus C0 divided by CSS minus C0, and this is the derivation that we set out to obtain. Here a equal to 1 minus t ln 1 minus Ct minus C0 divided by CSS minus C0. So in the build-up phase we have obtained this situation. If C0 becomes 0, then this becomes simplified because C0 we can use as 0. This is the build-up phase. There is a decay phase in which let us assume that the concentration had built up and the occupied space is now empty. So we do not have any internal source. See, here we had the internal source. Now the internal source is gone and only flushing is happening. So we have replacement air coming in and CO2 containing air going out, and we have the uh, air exchange rate as 1 minus T 1 minus minus 1 by T ln Ct minus Cr divided by Co minus Cr, where C0 is the concentration at the start of the decay phase, at which we remove the source and let the flushing happen. So now we can again derive this in the, as we have done for previously. So now we will again start our whiteboard. So let us say we have the concentration mass as m0, concentration as c0, where m0 is times 0. uh, I'll say mass and concentrations. Mass at time t, concentration at time t, and mt is related as v times ct, and mass at time 0 when our decay phase started is related to concentration at time 0. As previously we have F in, but this time we do not have any emission, we only have F out. Now F in is A V C R and F out is A V C at T. Now we have our dm by dt equation. So I will write dmt by dt equal to F in minus F out. This is A V C R minus A V C T, and I am going to write dm by dt here, which is A V V dct by dt. This is V dct by dt. So all the V terms will cancel out, and we will have dct by dt is equal to ACR minus ACT. So again I can start as ACR can be some term, so I will just put P minus ACT, where P is equal to ACR. So again here we have C at T. This is also again similar to the previous equation. So here again we can give Ct as C0 e to the power minus At minus plus CSS 1 minus e to the power minus At, where CSS will be actually CR, because if we solve this for steady state, let's say dc by dt equal to 0, a steady state dct by dt equal to 0, which means P equal to ACSS, and P is ACR, so ACR equal to ACSS, which means CR is equal to CSS. So basically we have again a very similar type of equation. Note that the solution to previous equation was Ct minus C0, CSS minus C0. We can do something similar here. So we have this equation now. Let me copy this to the next board. So Ct is equal to Ct is equal to C0 e to the power minus 80 plus CR 1 minus e to the power minus 80. So again we will do the same thing. So we need a term C0 minus CR. So we will just expand this. Ct is equal to C0 e to power minus 80 plus Cr minus Cr e to the power minus 80. So we have Ct minus Cr equal to e to the power minus 80 C0 minus Cr, because we have taken this and this terms here. So I will just rearrange this equation. E to the power minus 80 C0 minus Cr equal to Ct minus Cr, or minus 80 is equal to ln of Ct minus Cr divided by C0 minus Cr, or A is equal to minus 1 by t for any time t ln of Ct minus Cr divided by C0 minus Cr. This is our what we set out to derive. A equal to minus 1 by t ln of Ct minus Cr divided by Co minus Cr, what we have just derived. So now we have basically found out how to derive these air exchange rate or air exchange rate constants. There are of course some limits. So CO2 and ventilation standards and regulations in US and Europe have been sort of listed, and we have this country which is US, Europe, and here we have Portugal's and the guideline reference. This one is for teaching facilities and this one is for buildings and schools. So CO2 limit has been stipulated at 1000 ppm, and the ventilation rate for the setting in liters per second per person is 7, and for Portugal it is 8.3 liters per second per person. It is also sometimes guidelines are given as ventilation rates per second and air exchanges per second required to achieve a select CO2 level. So here we have age of the occupying people, so 7, 10, 15 years or adult, and this is their CO2 generation milliliter per second per person, 1.8, 2.6, 3.9, and adult are of course emitting the most. So if we have CO2 limit given as 1600 ppm for people of age 7 years and such this CO2 generation rate, we must give a ventilation rate of 9.2 liters per second per person. If we have adult instead of the child, so they are emitting more, so we have to give correspondingly more ventilation rate. Of course, if the CO2 limit is increased, that means we are allowing a worse quality. So if from 600 we increase the CO2 limit to 2500, we can reduce our ventilation requirement for adults 23.6 to 2.2, a substantial decrease in the ventilation rate. So as the age increases, we have to give more ventilation, but if we increase the allowable CO2 limit, then we can decrease the ventilation required, and accordingly for the given CO2 limit and the given occupancy, we can derive the corresponding ventilation rate from these guidelines. Similarly here, if you have stipulated area allowed for per adult, so this is area available in meter square per adult and the volume available per adult. So as the area available per adult increases, to achieve the same CO2 limit of 600 ppm, the air exchange needed in terms of per hour decreases from 34 to 0.85. So same way, if there is one adult in a huge room, we can probably have less ventilation because the CO2 will not build up as much. But if we had the same person in a very small space, the CO2 buildup will be higher, and then we need to provide a much higher ventilation. Then likewise as previously, if we allow more CO2 limit, then we can allow a less ventilation. So in summary, in this lecture, we have done the derivation of air exchange rates or air exchange rate constants estimated from a measured concentration of pollutant either in a build-up phase or in a decay phase. Now in the next lecture, we will look at the framework for ventilation rates and also some special cases.